This is where we were last time with the last video. So remember, there's two types of body waves, primary and secondary. The primary waves move the fastest of all of them. Then come secondary waves. So these are the two that go through the main part, the interior of the Earth. Although secondary waves cannot travel through solid because they move up and down. All right, so in other words, the thing that's waving, it waves up and down compared to the direction that they travel. All right, they're called transverse waves. These are called longitudinal waves. So the love waves, these are so here. So the surface waves. So there's love waves and Rayleigh waves. So the love waves oscillate back and forth, kind of like if you were just looking at the floor, imagine like a snake slithering along on the floor. Okay, so back and forth. That back and forth motion is what's called a love wave, and then the up and down motion right at the surface, of course, would be a Rayleigh wave. All right, let's move on. All right, so we just mentioned that the primary waves are longitudinal. That's important to remember that. That means, the wave, I just said it, but the wave is moving a certain direction. So let's say you're moving, along this sentence here, and that's the direction of the material waving. All right. So basically, a longitudinal wave will compress and expand the material, like sound, for example, is a longitudinal wave. The air molecules, if it's going through air, the air molecules will get compressed and then stretched, compressed and stretched. Of course, sound can also travel through water. It can travel through solid as well. And one other thing that's really important, we didn't really study sound, but I do want to bring these things. So if you just think about sound waves, right? So this is just a general statement about waves. People, measured the speeds of waves. So they measured the speed. Even Isaac Newton, going back 350 years, tried to measure and was more or less successful at measuring the speed of sound in air. And then afterwards, people realized, hey, we could measure the speed of sound in a liquid, in water, for example. That's the easiest to measure. If you use some large body of water, you can measure the sound. And they found that the speed of sound was faster in the liquid. So that's important to understand that it's slower in the gas, faster in the liquid, and then even faster when we were able to measure the speed of sound through a solid. And then when you talk about what the wave passes through, that's called the medium. So the denser the medium, the faster the denser would be, solid is denser than liquid, and liquid is denser than gas. So that's just an explanation of these variations in speed, which are going to become important to us when we talk about P waves and S waves passing through towards the center of the Earth. All right. Okay. So really important thing. The P waves are the only ones that can travel through solid and liquid. All right. Of course, they can travel through air molecules as well, but that's not present in the interior of the Earth. But there are solid and there are liquid, not water, but liquid iron and nickel, as we'll talk about that in just a little bit. So primary waves are the fastest of all. I know I've said this, and they're the first ones. When there's an earthquake, they're the first ones to be measured on a seismograph. All right. So, actually, let me show you a seismograph. There's a good a good picture of it here. A good picture of it in our textbook. Remember, you have an e-textbook, so you can. Oops, not that. Right here, right here. Okay, so here's a good example of a seismograph. This is actually the very first ones that were made. So the idea here is you have it's a very large mass of something, with lead or iron, something extremely dense is this mass, and and the important thing here is that it's hung on with a pendulum type of pivot point, so that it can pivot in any direction. That's really important, that it can pivot in any direction. All right. So what happens during an earthquake? Of course, the Earth is moving back and forth, but there's a principle that Isaac Newton taught us, called inertia. And so this mass, especially if it's really, really massive, and it can, this pivot point right here, can swing in any direction. So if what'll happen is, as the Earth shakes, the mass is at rest with respect to the Earth. It won't move. It won't move around. And if you, as it's shown here, if you tie a pen, or not tie, but attach a pencil or a pen to this, and then what the original people do, although we do it slightly, nowadays, of course, we do it electronically, but it's the same idea. You have this massive object, and because of inertia, it won't move around. But if you have so this is how they did it, 120 years ago, is you have this paper on a roll here, and you just roll it along at a constant rate, which we could do that 100 years ago. You roll it along at a constant rate, and then, of course, as I just mentioned, the P waves are the ones that show up first, and then the S waves, and then if there's any of the love waves or the Rayleigh waves, they'll show up as well. All right, so that's a seismograph, right? Because it's a graph. So we're actually going to do a lab on this, where we're going to look at some seismographic data of some earthquakes. All right, so let's go back to where we were. All right, very nice. All right, so secondary waves are transverse waves. So they're, if the wave was moving in the direction that I'm moving the cursor here, the thing that's waving is perpendicular to that. That's what we mean by transverse. So let's see. So the vibration of the rock is up and down, or side to side motion, and transverse motion occurs perpendicular to that as the wave travels. And in fact, that's exactly why it doesn't travel through liquid, right? Because as soon as it gets into the liquid, that energy, that up and down energy, doesn't go anywhere. Remember, it's got the longitudinal wave. The thing that's waving is going in the same direction, so that it'll go through. The P waves will go through solid and liquid. Anyhow, the secondary waves will travel through solid just fine, but they're unable to travel through liquid, for the very reason that they are transverse, right? Anyhow, secondary waves are slower than P waves, so they register second on the seismographer. All right, the surface waves are the slowest and the last to register on the seismograph. The Rayleigh waves have the rolling type of motion, so that's the up and down motion. All right, it's like as it says here, like the waves on the ocean. The tumbling occurs back and forth. compared to the direction of the wave, the ground will move up and down. All right. Love waves are similar to an S wave. That they're moving is kind of horizontal to the surface, side to side motion. It would be like if you had a whip right on the ground and you moved it side to side, or a snake, for example, moving across the ground. Although people generally don't like snakes too much, so. But anyhow, that's how these love waves go. All right. Most destructive earthquakes are caused by the passage of surface wave because they travel fastest. We know that's not true. They occur in the crust, the densest layer of the Earth. Well, the crust is certainly not the densest layer. It's in fact the least dense. That's why it's the crust. We'll get to that later. They occur at the surface where the ground shakes up and down and side to side. That sounds like the right answer. Let's read D for the heck of it. They travel deep into, no, they don't travel deep into the Earth. They're surface waves. Okay, so C is the correct answer. All right, let's see. Abrupt changes in seismic wave velocity reveal boundaries. Okay, so people started studying this right at the turn of the century. There's, if you read the textbook, and I hope you are all reading the textbook, they talk about various people. Most of those people, we're not going to have to remember their names or anything like that. This is not a history lesson. But each of them found these different boundaries. Okay, so the densities at different layers can be estimated by studying the velocities. Remember, if a wave goes from a solid to a liquid, or from solid to a liquid to a solid again, the wave velocity changes, and that can be detected. All right, that's this whole idea of studying these seismic waves. All right, as I said, mostly I'm not that interested in who did what. Okay, but they're just in 1906, this guy Oldham, observed that P waves and S wave travel together for a distance, and then encountered a boundary where the S waves stopped and the P waves refracted. So he had discovered the core mantle boundary. All right, so let's go back and take a quick look at that. All right, I'll come back. So he basically discovered right here down to about 2,900 kilometers below the surface of the Earth. So that's and the reason that he discovered that is because when the S waves got here, they die out, and then the P waves will refract. All right, so here, let's go back. Sorry, skip through here. Oops. I went a little too far. All right. So that's yes. So that's the next guy. Just generally, we call this boundary the Moho. That's what he observed. He observed in this guy was Czech from the Czech Republic. Anyhow, he observed a sharp increase in seismic velocity at a shallow layer within the Earth. So Moho had discovered the crust mantle boundary. All right, so basically he noticed that as the P or the S waves went from the crust to the mantle of course is more dense than the crust, and so it sped up. That's what he noticed, and so that's called that's very not very far underneath the surface of the Earth when you think about the distance to the center of the Earth. Right. So basically, what this guy discovered, this Moho boundary is where the crust ends and the mantle begins. Right? So the Earth is composed of a thin outer crust